Let's look at one more example. Say there are two work crews that repair similar aircraft components at a large aircraft maintenance repair and overhaul depot. The two work crews are Crew 1 and Crew 2. A sample of recent repairs was collected for both crews, 47 for Crew 1 and 39 for Crew 2. The mean repair time for the sample of jobs for Crew 1 was 56.9 minutes with a standard deviation of 13.2 minutes. For Crew 2, mean repair time was 48.4 minutes with a standard deviation of 10.4 minutes. Let's say we want to know this. Does Crew 1 take a longer time to repair this particular component than Crew 2? Assume that the data collection environment was the same for both crews and representative samples were collected. Okay, so we want to know, is the repair time for Crew 1 longer than that of Crew 2? Okay, so we go out and collect a sample of size N1 of 47 for Crew 1. Okay, sample mean repair time for the repair Crew 1 was 56.9 minutes with a standard deviation of 13.2 minutes. And for Crew 2, we collected a sample of 39 repairs. Mean repair time for Crew 2 was 48.4 minutes, and the standard deviation for that sample was 10.4. And we want to know, does Crew 1 take longer than Crew 2? Okay? Longer than implies strictly greater than. mu1 greater than mu2. Okay? That's equivalently written as mu1 minus mu2 greater than 0. Okay? Greater than does not imply equality. Equality must be in the null. So then this statement in the null is going to be the contradiction of this, mu1 less than or equal to mu2. And we could equivalently write that as mu1 minus mu2 less than or equal to 0. Okay, so we've got our hypotheses, we've collected our sample and found our sample statistics. And now we need to answer this set of hypotheses with a test statistic. Okay? First, before we calculate the test statistic, let's calculate the degrees of freedom. Remember here, we're assuming that these two values, these two standard deviations, are not equal to each other. Okay? When we assume they're not equal to each other, the degrees of freedom calculation is nasty. That's s1 squared over n1 plus s2 squared over n2, all of that squared, divided by s1 squared over n1 squared, all of that divided by n1 minus 1. Add to that s1, s2 squared, divided by n2, all of that squared, divided by n2 minus 1. Okay? We input all this stuff into here, and we get 13.2 squared over 47 plus 10.4 squared over 39, all of that squared, divided by 13.2 squared over 47, all that squared, divided by 47 minus 1. Add to that 10.4 squared, divided by 39, all of that squared, divided by 39 minus 1. If we work all of this out, okay, and we don't make any mistakes, which we shouldn't, the answer is 83.798, not an integer. Okay, we want to be conservative about this. Since this is not an integer, we're going to round down. So that's approximately 83. Okay? So now we have our degrees of freedom, 83. Now let's calculate our test statistic. The test statistic is how different is y1 from y2, our sample evidence, minus mu1 minus mu2. How different is the sample evidence from the hypothesized value in standard deviation units? S1 squared over n1 plus s2 squared over n2. Okay, so now we just got to input these values in. y1, 56.9. y2 bar, 48.4. And we're going to subtract off the difference, 0. We'll divide by 13.2 squared over 47. Add to that 10.4 squared divided by 39, and take the square root of that. Okay? How different is the sample evidence from the hypothesized value in standard deviation units? And if we work that out, we get a value of 3.34. Okay? So we've got an upper tail test. We've got a value on the t-axis for 83 degrees of freedom. We've got this test statistic of 3.34. Okay? If we wanted to find the p-value of this, since this is an upper tail test, the p-value is going to lie all up here. Okay? We're probably not going to find 83 degrees of freedom in our lookup table. So we're going to use Excel instead. And the function we're going to use in Excel is the tdist function. So our p-value here, we'll use the tdist function. Okay? We'll read in our test statistic the value on the axis, 3.34. We have to give it our degrees of freedom, 83, and whether or not this is a one-tail or two-tail probability that we want, and we want a one-tail probability. Okay? So this is what we've told Excel, and Excel, in its great wisdom, is going to give us back 0.00063. Okay? This is the p-value associated with this test statistic. P-value, very small, smaller than any alpha that we might ever choose. We are going to reject the null and conclude that crew 1 does indeed have a longer mean time to repair than crew 2. With a quite high amount of confidence. This is a very small p-value. We have a lot of confidence that the mean repair time for crew 1 is indeed greater than mu2.